Hello and welcome to lecture 26 of the course Theory of Computation. In the lecture 25, the previous lecture, we saw pumping lemma for context-free languages, right? In this lecture, we'll see some examples for the same, right? For pumping lemma for context-free languages, right? So just to recap, the statement is that if A is a context-free language, then there is a pumping length P, such that if you take any string in A which is of length at least the pumping length, we can divide the string into 5 parts u, v, x, y, z, such that the below 3 conditions are satisfied. So what are the 3 conditions? First condition is that for each I, u, v power I, x, y power I, z is in A. So this gives an infinite class of strings including u, x, z when I is 0, or u, v, x, y, z when I is 1, or u, v, v, x, y, y, z, and so on, right? So these are the strings that it says that all of these strings belong to A. Second condition is that vy is the length of vy is strictly greater than 0. In other words, this means that either v is non-empty or y is non-empty. So both of them cannot be simultaneously the empty string. And the final part is that vxy, length of vxy is at most p. And these are the 3 conditions. So as very much like pumping lemma for regular languages, we cannot use the pumping lemma to show that a language is context free. What we can use it to show that a language is not context free. So the way we will do it is we'll assume that the language is context free. So then that will give us the fact that there is a pumping length, some pumping length p, and then we will choose a string, right? And then so this choice of the string is usually the most creative step. And then for that choice of string, all right, so we'll have to come up with a string which cannot be split in a way that satisfies these conditions, right? So every time the choice of the string is usually interesting, and that will help us show that the language is not context free. So let us see the 2 examples. The first example is that B is a power n, b power n, c power n, right, for all n greater than or equal to 0, right? So this is the language of strings. Let's say empty string abc, aa, bb, cc, then aaa, bbb, ccc, so shortening as a cube, b cube, c cube, and so on. It's an infinite set of languages. We are saying that B is not context free. So how can we use pumping lemma to show this, right? So first step is to assume that B is context free. So then that means that there is a pumping length as per the pumping lemma. So let P be the pumping length. Now the string that we will choose is A power P, B power P, C power P, right? So P A's, P B's and P C's. Now we'll show that this string cannot be split in the way that we want. So let S be, let's say we can split it as u, v, x, y, z, right? And so this is the string that I've just written in like kind of expansively here. And now we'll show that whichever way we choose v, x, y or u, v, x, y, z, it will violate some condition or the other. So let's see, the first case is this. Suppose v is like this. Suppose v ranges in this part of the string, right? So the way when I say this part, I mean v kind of spans both A and B. Now if you consider what will happen when I take u, v square, x, y square, z, right? So now if V has both A's and B's, right? So now U is entirely A's, and then we have V which has A's and B's, right? This is V, and again another v, so again it has a's and b's, right? And then xyz, right? So x is again some b something, and so on. So now notice that you have some a's followed by some b's followed by some a's again, then followed by b's. So now you see that it is not of any not of the form some a's followed by some b's followed by some c's. So notice that the language B is actually a subset of A star, B star, C star, and this u v x y square z, right, is not of that form. It is not of the form A star, B star, C star, because V is spanning both A's and B's, right? So this means that V cannot span both A's and B's. Similarly, V cannot span both B's and C's also, because then again it will not be of the form A star, B star, C star. Similarly, Y also cannot span the boundary of A's and B's or the boundary of B's and C's. So if V or Y contains two types of symbols, which can happen in this way only, then u v square y u v square x y square z is not of the form A star, B star, C star. So which means all of v and y are of only one type of symbol, right? So v and y cannot span the boundary. So v and y are both only one type of symbol. So which means, let's say v could be entirely b's and y could be entirely c's, or v could be entirely b's and y also could be entirely b's, right? Or v could be a's and y could be b's, right? But this means that V contains some set of symbols and Y contains some another set of symbols. So we have three symbols, right? A, B and C. V can only contain one type and Y can only contain one type. So which means that let's say V contains only B's and Y contains only C's, which means A's are not in V or Y. Then if you consider the string u v square x y square z, this will have more B's than u v x y z. This will have more C's than u v x y z, but the same number of A's, right? So it may have more B's or C's, but the number of A's remain unchanged, which is again not part of the language, because the language contains A star, B star, C star with the same number of A's and B's and C's, right? So V and Y can only contain one symbol each. So V could contain A, Y could contain B, then C is not there. So then u v square x y square z contains A's and B's, and that is more than the number of C's, right? Or if V and Y are both A's, so then u v square x y square z has more A's than B's, right? So whichever way you take, V and Y cannot span all three symbols, and hence either it loses in structure or the count. So whichever be the case, the resulting string is not in the language B, hence the language is not context free, right? So whichever way you take the split, the resulting u v square x y square z is not in the language. So hence B is not a CFL. So it is kind of small amount of curiosity is that the language that was not regular that we used to that we saw first was this language 0 power n 1 power n, or I could say a power n b power n, right? So a power n b power n was not regular, but we saw that it is context free. But a power n b power n c power n is not context free. So that is kind of somewhat amusing. When you want to match two symbols for equal count, then you cannot do with regular languages, but then you can do with context free languages. But when you have three symbols and you want to match them up, even then you cannot do that with a context free language, right? The next language that we want to show as not context free is a power I, b power j, c power k, where the number of i's is less than or equal to the number of j's is less than or equal to number of k's. So you have again this is also a subset. This is also a subset of a star, b star, c star. But here the number of a's must be less than or equal to the number of b's, which must be less than or equal to the number of c's. Right. Earlier we wanted the counts to be equal. Here we want the count to be number of a's to be less than or equal to number of b's, less than or equal to number of c's. Right. So again we assume the same thing. We assume that it is context free, which means there is a pumping length p. Okay. And the string that we consider is actually the same string, a power p, b power p, c power p. So it is of the form a star, b star, c star, and the number of a's and number of b's and number of c's are equal, where equal is allowed, right? We just want I less than or equal to j, less than or equal to k. So equal is allowed. It cannot be that number of a's cannot be more than the number of b's, or number of b's cannot be more than the number of c's, right? This is the point here. So I have written the string kind of expansively here, right? So again, let's try to reason why this cannot be split as u, v, x, y, z. Right? So once again, like before, suppose v was in this boundary, or v was in this boundary. Then when you consider u, v square, x, y square, z, it will be of the form. So let's just take v in this place. Right? Then u, v square, x, y square, z will have some a's followed by some b's, again followed by some a's, then some b's, and so on. So this is not of the form a star, b star, c star. Right? So if v or y spans the boundary, meaning contains two types of symbols, then u, v square, x, y square, z is not of the structure that we want. Structure meaning it is not of the form a star, b star, c star. This means v has to be only one type of symbol and y has to be only one type of symbol. So now there are multiple possibilities. Both v and y are a's, or both v and y are b's, right? So we'll consider all these possibilities. Earlier we wanted all of them to be same count, and then we could find a contradiction easily. Here it requires a bit more work. Okay, not too much more work, but slightly more work. So let's first assume that, so there are different cases. V and y contain only one type of symbol, right? V could contain one type, and y could contain, need not be the same type, maybe a different type. But then there we have a and b and c, which means one of these three symbols has to be avoided. So let's say vy avoids a. So these are the three cases. Let's say vy does not have any a in it, right? Which means either v could be in b's and y could be in c's, or both of them could be in c's, anything, right? Now consider the string u, v power 0, x, y power 0, z, meaning from the original string s. So s was a power p, b power p, c power p. I am removing a copy of v and removing a copy of y. I know that vy is non-empty, which means either I am bringing down the number of b's or the number of c's in the string, because if v or y, if they avoid a, they must contain b's or c's, and we know it's not empty. So either the number of b's or number of c's should come down, and in the string s, number of a's, b's and c's are all equal. And now when you bring down the number of b's or the number of c's, right, it makes the number of b's less than the number of a's, or the number of c's less than the number of a's, which means the resulting string is not in the language capital C, right? Because the number of c's has to be greater than or equal to number of b's, which has to be greater than or equal to number of a's. So if vy avoids a, then you pump down, meaning you remove v and y. If vy avoids b, meaning, right, vy could be either c's alone or a's alone or A and C both, right? So we'll consider both the cases. If Vy avoids B but contains A, right? Now consider U V square xy square z, right? So by assumption it contains A, which means when you pump up, the number of A's goes up. Number of B's is unchanged because V and Y does not have B. So number of A's and B's and C's were equal in S, right? Number of A's, B's and C's were equal. Now number of A's goes up but B's remain the same, which is again not as per the rules of the language C, right? So if Vy avoids B but contains A, then uv square x y square z is not in the language. If Vy avoids B but contains C, right? So we don't know about A but it contains C, then you pump down. So it avoids B but contains C. So when you remove Y and V, then there is a reduction in the number of C's, but the number of B's remain the same. So it has more B's than C's, which is not allowed as per the language, right? So this is the issue when Vy avoids B. Now if Vy avoids C, right, now you can pump up again. So which means V and Y contains A's or B's or both. Now when you pump up, either the number of A's or the number of B's goes up, right? So it need not necessarily contain more A's, contain more A's than C's or more B's than C's. So if Vy avoids C's, then when you pump up, either A's goes above the number of C's or B's goes above the number of C's. So whichever one it avoids, A, B or C, then you can accordingly pump up or down and get a string that is not in the language C. So again, this language C is also not context free. Right? Hence, C is not context free. Right? Now, so we saw two languages. Now, finally, we'll just state one more example, which I will not work out here, but I'll just leave as an exercise. So consider the language D, where you have W followed by a hash symbol followed by W, where W is entirely comprising of zeros and ones, binary. So you have some string followed by hash followed by some other string. So it could be something like 01 hash 01, this is in the language, or 111 hash 111, right? So all of these strings are in the language, but something like 0 hash 1, this is not in the language. So set of all such strings that are in the language, so this language is not context free. And in fact, this is similar to some exercise in the book, example in the book, worked out example, where it is WW without the same thing without a hash symbol. So the same string repeats twice, the same binary string repeats twice. It has, in the book they have worked this out, so you can go through the example and see how we can maybe modify this proof for the language D. And that's all that I have for as far as examples of pumping lemma for context-free languages are concerned. Right. So we restated the pumping lemma and saw two examples. In both the cases, the template is the same as what we saw in regular languages as well. We assume that the language is context-free. Then, as a result of that assumption, we get that there is a pumping length. And using that pumping length, we choose a string. So this has to be carefully chosen. And this string has to be chosen in such a way that whichever way you try to split this string as u, v, x, y, z, it will violate some condition or the other. And and then we saw the two examples. And that's it as far as lecture 26 is concerned. Uh, and this also completes the part on context-free languages, right? So we saw regular languages in chapter 1. This is the end of chapter 2, which is context-free languages. We saw context-free grammars and PDAs, Chomsky normal form, etc. And now we are seeing pumping lemma. And this completes the part on context-free languages. What comes next is Turing machines and the beginning of computability theory, right? So see you in lecture 27 with the beginning of computability theory and Turing machines.